All right, so I'm going to show in this video how to solve the multiple reactions in a PFR problem using the matrix method and Python. So this is the same problem that we solved in a CSTR and then also wrote out the solution for a PFR. I'm going to make the minor difference in this solution that I'm going to use this matrix method. So basically this is a code I'm using. This is going to set up a function to solve a PFR with multiple reactions, an isothermal PFR with multiple reactions. I've copied the given information in from the CSTR notebook that I shared with you earlier, making the one change that now that it's a gas phase reaction, whereas in the CSTR it was a liquid phase reaction, we have in this gas phase reaction we have a lower initial concentration by about 1 order of magnitude. The stoichiometry matrix is the same. The initial concentration and flow rate matrices are the same. One thing I'm going to need, since this is a gas phase reaction, for my concentration equations, I'm going to need a value for the total concentration initially, CTO. I can get that by summing this initial concentration vector, which is what I've done. I'm printing out some information just to make sure I've done everything correctly, and here's my PFR function. So some differences here about the input arguments, or I guess some similarities and some differences. Both are going to have this x variable. The PFR requires a independent variable, that you specify an independent variable. I call this PFR vol. It's defined down here. PFR vol is basically this. It's going to give points between 0 and v, where v is the volume that we specified above. This is going to tell the ODE solver what to integrate over. So I have to specify this. If you do not specify this term here, you're going to get errors. The Python is going to tell you or give you errors about maybe the dimensionality of something. I can't remember exactly what they are, but this is important. My input arguments, so in my CSTR, I had to tell it the inlet molar flow rates, I had to tell it the inlet volumetric flow rate, and I had to tell it the reactor volume. I don't have to do that here. So the reason I need to do that in my CSTR is because those quantities are involved in my mole balance. Those quantities are not involved in my mole balance for my PFR. So I'm going to delete those from my input arguments, and I'm only going to pass through my stoichiometry matrix, my total concentration initially, and then my rate constants. This terminology here is the same as in the CSTR. So basically, the variables that I'm going to solve for, I'm going to call those x, but I'm going to assign columns within this x matrix to my different flow rates of my different species. Another thing I need here, because I have a gas phase reaction with a change in the number of moles, is an expression for the total molar flow rate. So I'm just going to add that up. All right, so here's my concentration equations. These are going to be different than in the liquid phase case that we looked at in the CSTR, because this is a gas phase. This is a gas phase reaction. I need this initial total concentration, and then I need my mole fractions at any point along the PFR. That's what these equations are. My reaction rates are the same as in the CSTR case. My net rate expression is the same as in the CSTR case. I'm going to return my net rates, but I want to get rid of the array character. I don't want any dimensionality there, and that's because the ODE int solver doesn't want that, so I'm going to use this flatten command. You can just probably ignore that. This, as I said before, are the values I'm going to be integrating in between, and that's already set up. Now I'm going to call the ODE int function. I'm going to call it on PFR. I'm going to give it my initial conditions. So I'm solving this for flow rates, so I have to give my initial flow rates, which I've set up here. I'm going to tell it what to integrate over. These are my 3 required arguments here for the ODE int function, and then these are the arguments that I'm going to pass into the PFR function. And these must be in the exact order, that they must be the exact the exact variables, and also in the exact order as they are right here. And if you don't have that, then you could get errors. Okay, so basically then this code right here is going to solve for it's going to integrate the ODEs and provide a solution. It's going to give us it's going to give us vectors of values for the flow rates of the different species along the reactor volume. I want to extract those out of the solution here. I do this by extracting out the different column vectors within the matrix. This is what this notation says. So this says I want my 0 indexed column. That's the first column in the matrix, but I want all the values. And this, for example, says I want the 1 indexed column, which is the second column, and I want all the values, etc. So once I have those, I can rebuild my total molar flow rate. Remember that I do have this function or this equation up here, but if it's inside the function, it doesn't apply globally. So I have to redefine it based on the values I have. So I do that. I redefine my concentration equations. And then here, I'm going to need to plot my solution. So in the CSTR case, I just get one answer. PFR, I have everything changes as a function of volume. So I'm going to plot that solution. Specifically, I'm going to plot the concentrations of the different species. So if I go and run that, this is what I get. This is the information that I printed out initially to basically check. So I print my stoichiometry matrix, my inlet total molar flow rates, and then I also printed out my total inlet concentration just to make sure that I entered all that correctly. And then here is a graph of the concentrations of the different species versus PFR reactor volume. And that's it.